All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Preston Culbertson, who is an incoming assistant professor of computer science at Cornell University, and he will start in fall 2025. By the way, Preston will be soon hiring. He will have some details about it, so if you like this stuff, consider contacting him. So something about Preston. Preston received their PhD in mechanical engineering from Stanford, where they were working with Max Schwager, and currently is a postdoc in the Amber Lab at Caltech. Preston's research focuses on risk awareness in robotics, leveraging tools from machine learning, computer vision, and control theory. And the goal typically is to develop robust, contact-rich robot behaviors for tasks that are challenging, for instance, manipulation and locomotion. Today's talk is centered around these topics and is titled "To Err is Robotic, Enabling Robust Autonomy with Risk Sensitivity." And I'm very excited to hear more about this new line of research, and I assume the audience as well. Feel free to ask questions during the talk. I will monitor the chat and also give you the word in case you want to ask directly. So without further ado, Preston, go ahead. The stage is yours.
Perfect. Thank you. Yeah, I'm really excited to be here and talking today about some things that we've been thinking about, especially on the lines of like uncertainty and kind of risk sensitivity for robotics. So my background is really in sort of what you would call like maybe classical or like model-based robotics. So I've worked a lot in kind of like nonlinear control. And so, I want to start today's talk by thinking about, especially for tasks like manipulation that are, kind of dynamic and contact rich, places where these like model-based classical techniques work and where they don't, and when they don't, how we can fix them using maybe ideas like risk sensitivity. And so to start, I want to start actually with some kind of older work that at least at Caltech, a lot of the graduate students are less familiar with. So this is a seminal paper in manipulation from Ken Salisbury and Jean-Jacques Slotin called Whole Arm Manipulator Catching. So I'm going to play the video. So basically what's going on here is there's a student off screen who's throwing this orange ball to the robot. And the task is basically just catch the ball. And what I think is interesting about this video is a couple of things. First is this video, or like this controller, is basically purely vision-based. So up here in the top of the screen, there's actually two gimbaled cameras that are tracking the motion of this ball using just like 1990s computer vision. And the second thing I want to point out is that basically, if you look at the performance of this thing, really the motion of this is quite dynamic and quite exciting, I would say, right? This is a task that, especially for humans, this like pure vision-based catching can often be tricky. And using basically a purely model-based stack, using 1990s compute, 1990s computer vision, they're able to get really, really, really robust and really dynamic catching, which I think, again, for a lot of us might be surprising in terms of how good the performance of the system can be, with no learning, no kind of fancy tricks being played here. And actually, a big part of this is because the dynamics of the system are easy to model, right? Like, especially this ball is going to move like a parabola, and so that's easy to predict. But they actually extended this work, I would say more famously, to do paper airplane catching. So here, they're actually basically training a neural network online. Like, they're using adaptive control techniques, but basically it's the same setup, right? There's this vision system that's tracking that red piece of tape you see on the paper airplane. They're adapting the dynamics of the airplane online. And again, they're able to get this really dynamic motion out of this thing, right? They're able to basically like snag this paper airplane in real time, which I think is, again, really exciting and maybe somewhat surprising in terms of what you can do with model-based techniques. But if you change the task just slightly, and in particular, if you introduce contact, what you get is basically a task that model-based techniques, I would say, don't work so well on. And really the state of the art. So, I mean, I'm showing here a video from OpenAI from a project called Dactyl that they did in like 2018, 2019. Pulka Agrawal is doing, I would say, even better work than this right now at MIT. But basically, the only ways that we're seeing folks able to do this kind of like dexterous in-hand manipulation is not really using these model-based techniques that maybe I'm familiar with and some of the controls community would use, but it's actually using just reinforcement learning. And what you can see is that basically, you're trading maybe the simplicity of these stacks that we were seeing working for catching for a really complicated stack that also gives you maybe less dynamic motion than we would hope. And so, kind of a question that's shaped my work is basically, for one thing, why is this so hard, right? why is it when we try to apply maybe these like model-based, like classical techniques to a problem like, dexterous manipulation or contact-rich manipulation, do these techniques fail? And really, are there ways forward for using these kind of model-based techniques in the future? So one argument that I'm going to make in this talk is a big reason why our classical tools fail for these contact-rich tasks is uncertainty. So in particular, I'm going to explore in this talk uncertainty along a couple different axes. One important one is dynamics uncertainty. So I think it's not super controversial to say that, especially for these contact-rich tasks, our contact models are not great. And in general, especially for long horizon prediction, they don't do very well. Especially, for things like manipulation and bipedal locomotion, let's say, there's also lots of under-actuation in the task. So, if you want to draw basically contrast between maybe the system that works to something like robotic catching using these classical techniques and places where our classical techniques start to struggle, one big thing is basically that it's hard to model the harder systems. And this under-actuation makes it sort of chaotic, right? Quickly, our trajectories will kind of diverge if there's a little bit of error in our model. Another one that I've been particularly interested in that I think pops up especially in manipulation is something like geometric uncertainty, right? A big part of the problem is that if you want to have a system that's able to manipulate a wide variety of objects, you need to handle basically this kind of like shape estimation and pose estimation problem that really hinges a lot on computer vision. And so I think really one argument I want to make is that the reason that dexterous manipulation has been so hard, especially for model-based techniques, is that it combines these two types of uncertainty that we're already like pretty bad at handling. It basically requires us both to be able to be robust to uncertain dynamics and also to be robust to like visual ambiguity or like geometric uncertainty. So a lot of my work has been focused on ways that we can still use model-based techniques to do these kind of like hard contact-rich problems, but being able to tolerate these types of uncertainties that we encounter in real-world systems. And so in particular, a lot of my work takes a kind of similar approach, which I would call risk sensitivity. So basically, a lot of my projects, the way that I try to approach these really hard kind of real world like tasks is basically to first try to explicitly model the uncertainty that's present in our system, right? So typically this is using data-driven techniques, but in general, what I'm interested in is something that you might call like real to sim or, model calibration, but basically finding ways we can model actually not just nominally what the dynamics will be, but actually the kind of range of things that we'll see as we operate our system in real life. And then second, to combine these with robust planners and robust controllers, right? So if we have an understanding of how, our uncertain system is going to move, finding ways that we can design motions for the system that will be robust to this ambiguity. And I think the benefit that you get from this approach is basically, you get the benefits of sort of model-based approaches, you get the benefits of having ideally well-calibrated models of how your system's going to move. And hopefully what this leads to is ways that you can operate robots robustly in real life. So like I mentioned, I'm going to use this kind of chart to structure the talk today. So what I'm going to talk about is, unfortunately, not a lot of dexterous manipulation, although we'll loop back to some work that we have ongoing at Caltech right now, trying to use these techniques to do something like dexterous in-hand manipulation. But really what I'm going to focus on is first ways that we can handle these uncertainties separately. So in the first part of the talk, I'm going to talk about new tools from 3D computer vision that we've been using to handle geometric uncertainty and like visual ambiguity. So this has been a big problem that we've been looking at, especially in the context of like visual navigation. And then in the later part of the talk, we're going to switch gears. So instead of thinking about like visual or geometric ambiguity, we're instead going to think about uncertain dynamics. So this is almost like the second part of that like risk sensitivity plot I showed last time. Like what we're going to do is think about new robust control tools that we can use that even when our system is uncertain, even when we don't, perfectly know how it's going to move, we can still build robots and still build systems that are robust to those ambiguities. So again, I just want to say, if anyone has questions, if anyone has comments, feel free to jump in now. I'd be happy to, just go back and forth in the middle. Cool. Okay, so if not, I'm going to jump in now to the first part of this talk, which is focusing on new 3D computer vision that we can use to handle geometric uncertainties. So In particular, the problem we're going to focus on for this part of the talk, again, it's not manipulation, but it's actually something that I think is just almost purely a visual problem, which is visual navigation. So the problem setup is as follows. We're going to take a robot, think like a quadrotor, and we're going to place it in this like uncertain environment, but we're going to equip it with a camera. And basically what we want it to do is just go from point A to point B, right? We want to plan a path and track a path that moves through this uncertain environment using only its visual feedback without colliding with any of these obstacles in the scene. And what I would argue is kind of the key challenge, or maybe the key design decision of a visual navigation stack, is basically how we represent the obstacles that we're trying to avoid in the environment. So our representation is going to need to both represent the sort of like occupancy of how the obstacles are placed in the scene, but then also, we need to be able to construct this representation easily using just the onboard vision equipped with the robot. So to formalize this problem a little bit more, we're going to consider a robot whose body I'm going to label B, right? So it occupies some 3D volume. And what we want is basically the robot to stay out of some obstacle set O. So what we want is to plan a trajectory for the robot through the environment where the distance between the robot body and the obstacle set for all time is greater than 0. So this is great. This is just kind of normal, I would say, trajectory optimization. The hard part of this problem is that we don't exactly know what our obstacle set is, right? Because we're building this obstacle set ideally online using vision, we're going to have some uncertainty or let's say ambiguity about where the obstacles are. And so what this means is that we don't actually have a normal kind of deterministic trajectory optimization, but instead we're going to pose this as what you would call a chance constrained trajectory optimization, right? So instead of constraining, like with probability 1, that our distance between our robot and our obstacles is greater than 0. Instead, what we want is that the robot stays out of collision with high probability. And so we're looking for ways that we can represent the obstacles to be able to enforce this constraint in our trajectory optimization. So I would argue the reason this is hard in general is basically it's the construction of these obstacle sets, right? So what I'm showing right now is actually Chimera. It's a great kind of semantic SLAM pipeline put together by Luca Carlone's lab at MIT. This is kind of, one of the, I would say, state-of-the-art kind of semantic SLAM systems, which is great. But one thing I want to point out is if you peel back if you open the hood of this thing, really, a lot of our SLAM systems that we use, that you would just like get cloned basically, have a ton of decisions, like design decisions that are going on in the back end, right? They're extremely complicated. They're extremely, there's tons of different like heuristics and things that are put together so that basically, if you want to be able to operate a system like this, in general, you're typically trading off a lot of different, let's say, desiderata to basically be able to get the system to work, especially in real time. And one tension that I want to pull at is basically, again, kind of the fundamental design decision for a visual navigation stack is how you're actually representing your obstacle geometry. And typically, there's kind of this tension between two things. One thing is being able to reason about collision, right? So there's lots of geometry representations, like, say, occupancy grids, that are great for letting you reason about where your robot's going to collide with things and where it won't. And typically, these things are in tension with the sort of representations that are good for state estimation, right? So something like point clouds, let's say. And so one, kind of tension that we wanted to pull at is basically, are there scene representations that are maybe good at both? Are there ways that we can kind of get a free lunch and be able to both find a representation that blends well with the vision stack and also lets us reason easily about collision? And so kind of the core idea was to use actually new tools from 3D computer vision, and in particular to use one called a Neural Radiance Field, or a NeRF. So I should point out, actually, what I'm showing on the right is one of these things training in real time. This isn't actually a NeRF. This is a newer tool called Gaussian splatting, but it's all kind of the same math under the hood. So the core idea is basically these representations, you train them from a set of posed images in the scene, right? So here, like what we're looking at is actually, I trained this using a set of photos I extracted from an iPhone video of this like manipulation setup. And so basically what we're doing is we're performing what you would call inverse rendering. So basically we're training a representation that's going to map 3D points in space and a view direction. So basically, a point, a direction along which we're viewing this point to a density and a radiance. So the way I like to explain this is basically we're going to represent the world as colored fog where the color can actually depend on basically the direction at which you're looking through the fog. And the reason you do this is basically, A, it's really easy to train, right? So this thing is actually training in real time. And B, it lets you basically perform this rendering process really quickly online. So basically, again, like what we're looking at is actually if you perform rendering. So basically, if you take a synthetic camera and you cast rays through the scene, and you basically do some math to figure out what the fog would look like from particular viewpoints, what you could do is actually generate synthetic images of your scene that you can use for lots of interesting downstream tasks. So things like pose estimation, things like semantic queries, et cetera, et cetera. So the reason we were excited about this model is first, of course, this like generative visual thing, right? It lets you basically hallucinate what the scene will look like given different poses. And so, yeah, you could play these games of like, oh, you can use this for downstream tasks like pose estimation. But I think there's also a lot of interesting properties of these sort of like rendering-based representations. One is that I would argue the fogginess of this is maybe a feature and not a bug, right? So actually, because like places that are visually ambiguous, right? Like you can see in this scene, even like places that we haven't viewed too clearly are kind of fuzzy. It gives you a way to basically reason about the uncertainty that's present in your scene, which is something that we'll pick at as part of this project. And of course, I think a big thing is that it's easy to blend with computer vision, right? It's basically directly supervised using raw images, which means that you don't even need depth information to be able to stand up something like a SLAM pipeline on top of this. We're, of course, not the first people to think about applying NeRFs in robotics. There's been lots of great work, especially this work, block NeRF that came out of Waymo, I think is really exciting, where they trained a NeRF of roughly San Francisco, and were able to handle like lighting changes and dynamic, scenes and this sort of stuff, basically using embeddings. But overall, what we were interested in is finding specifically ways that we could use NeRFs to do something like visual navigation. So I would say problem setup for this paper, so this is an RAL paper that appeared in 2021, is we're going to assume that actually the NeRF is trained offline. So basically, the problem setup now is going to be that the robot has already built a NeRF of the scene. And what we want is, given this NeRF representation, to see if we can find a way that the robot can navigate from point A to point B without colliding. So what we need to do is first find ways that we can plan collision-free trajectories through this NeRF. And then second, find ways that we can actually track it. So if we have disturbances to our dynamics, et cetera, ways that we can do basically state estimation in real time. So one asterisk I want to add here is that basically for convenience, we're assuming that we have access to the NeRF. A question I get a lot is basically, why can't you train it in real time? The answer is basically now you can. There's lots of people doing NeRF SLAM work where you can put together a full SLAM pipeline using this. But back when we were doing this project, NeRFs took like a day to train. And so we just assumed that you'd train the NeRF offline and then wanted to use this to do kind of visual navigation. So like I mentioned, there's kind of two steps of this. There's the tracking, so there's the pose estimation, and then there's the planning. And so it turns out you get the pose estimation roughly for free by choosing the NeRF as your visual representation. So basically what we proposed is a like gradient-based pose estimator. So the idea is that, at each time step, your robot's going to get an image of the scene. So here, if we're looking at this GIF, that's what we're going to show as like the solid image. And then what you can do is, given your like current pose estimate, you can render what the image would look like from different poses, and you can basically do MAP inference, right? You can descend on a like visual reconstruction loss to be able to refine your pose very quickly to kind of line up where you think your robot is and where the image you took was, to basically be able to do, again, like vision-based data estimation. So again, this is kind of the easy part. The harder part is basically how you can actually do like trajectory optimization, how you can do this kind of like chance constraint thing I showed a few slides ago. And really what that requires is that you have to define collision with a NeRF, or essentially you have to say, if my robot's moving through this like fog world, how do I know if I'm, like hitting enough fog that I should call this a collision? And so our core idea here was to actually repurpose some of the math that comes from the rendering of the NeRF. So basically, the idea is when we're performing these rendering processes that we were showing before, right? If you look along a particular ray as you're kind of casting it through the fog, what you can, like if you peel back the math that's underlying this NeRF, what you can do is actually reason about collision probabilities. So you can say, if I, look along, say, this bendy ray, if I take a point and move it, from point A to point B, you can just look, like using the NeRF density, there's a way to compute the probability that that ray terminates. And actually that probability is how you perform rendering. You take an expected termination distance. I see there's a question in the chat.
Yeah, HM asks, how big can this offline mapped area that you're mapping with NeRF be? And also, what's the impact on memory usage?
Yeah, that's a great question. So in terms of size, like again, Google got their map up to like city scale. So they're able to map a full like San Francisco map. Like the way they were doing it was actually stitching together. I think each NeRF corresponded to about a city block. And so they trained hundreds of these that they kind of stitched together. The memory usage question is interesting. I think typically it's fairly lightweight. So I think for instance, the model that I was training with the Gaussian splats was typically the like NeRFacto model that you'll see out of one of the big like NeRF Studio, like one of the kind of common NeRF packages. Those train to be about 250 megabytes or 500 megabytes. So they're not lightweight necessarily, but I think especially compared to something like occupancy grids or other kind of voxelized representations, they tend to be lightweight. And I think there's also lots of ways to, especially using newer representations, like compress this information. But yeah, at least for size, there's already like good proofs of concept of basically, like my advisor Mac also has been doing this over like Lake Lagunitas at Stanford. So it's like you can get, actually pretty good sized areas. And especially if you start chopping it into multiple NeRFs, you can make it, I don't think it's too loose to say you can make them pretty arbitrarily large. But that's a great question. Yeah.
Oh yeah, HM says thank you. So the question was answered.
Great. Okay.
Satisfactory.
So, basically, so yeah, you have all these nice properties of, it should be memory efficient and blah, blah, blah. The issue is basically, again, how do you define collision? Like, how do you actually say when your robot's bumping into something? And so our core idea is basically, yeah, if you take a point on the robot and you trace its path, so say this is like a perspective like motion of the robot, you can use actually the NeRF rendering math to get a collision probability. And so the core idea behind this part of the project is basically, if we assume that ray termination under the NeRF rendering is equivalent to like physical termination, so basically the probability that this physical point on the robot will bump into something, then you can kind of repurpose this like NeRF ray termination probability as now a collision probability for our real robot. So I'd say this is a medium strong assumption. There's an important like edge case, which is when you have transparent objects, right? Your ray will continue through the environment, but if you had like a window, your drone would not continue through the window, or at least not well. But if you especially have an environment with lots of kind of specular opaque objects, this should be totally fine. And so the kind of core idea here is basically, now if we want to reason about the probability, not just of one point on the robot like terminating, but if you want to reason about the whole robot, what you can do is represent your robot as a point cloud and then compute for all of these points as you move the robot along a trajectory, what their collision probabilities are. So the last step is basically, once you've computed these collision probabilities, you can invoke the union bound, which is loose, but sort of helpful to basically say, if you sum up all of these collision probabilities, this should upper bound the chance that your point cloud robot actually collides with something in the environment. So one thing I'll say is that this is fairly loose. There's a couple things going on, right? First is we represented the robot as a point cloud, but it's not, The second is that this union bound is also quite loose. But I'll talk in a few slides about some math that we've been, like another TRO paper that we've been putting together that has maybe a bit tighter way of doing this. But for now, we're going to start with the first thing that we tried, which is this union bound thing. What we're going to do is perform kind of risk sensitive path planning. So basically, what we're going to do is optimize this like two-term cost. The first is just a very vanilla like LQR control penalty. And the second is this collision probability that I proposed in the last slide. And basically what you can see is that when you optimize this thing, what you get is actually kind of the performance you would hope for, right? This region in black is a region of high density and like a 2D NeRF. And what we're doing is basically optimizing for these points that you can see seated in this rectangular robot. We're optimizing this loss. So what you can see is that you get this nice trajectory that's both smooth, like dynamically feasible for its like non-holonomic dynamics, and also avoiding collision, right? So it's doing kind of what you would hope. So this is the whole pipeline working in real time. So basically what's happening is we first perform just like an A-star search through the environment. We use this as the initial guess for our planner, and then we use gradient descent from there to basically refine this into like using that trajectory loss I showed on the last slide into something that ideally should be both smooth and also avoid collision. And so what I draw your attention to especially is this kind of like top pillar that you see close to the green square. You can see that basically this NeRF collision loss is actually pushing the robot out of collision to move like directly through the middle of this pillar. And we found in the paper, we have some nice results showing that if you look even at like ground truth mesh intersection, that this NeRF collision loss is in fact getting the robot to actually avoid collision with the real objects, even though it's just based on this like fuzzy NeRF loss. So then we can return to kind of the whole problem, right? So basically, we want to perform both state estimation and planning. And obviously, when you put these together, you can run them in the MPC fashion, right? You can continually recompute your trajectory using your current state estimate. And so what we did is basically had our robot fly through an environment with a disturbance applied. So here, this is like this playground environment. We have you can think of it as wind blowing to the right. And what you can show is that basically, if you're performing this kind of recursive state estimation and planning, you avoid collision, which is what you'd hope for, whereas your initial plan, is going to get pushed off and collide with the environment. So overall, I want to emphasize this is basically, this first RAL paper was like a nice proof of concept that basically NeRFs could be useful for visual navigation. Like it is possible to stand up both a state estimation stack and a planning stack using this kind of like fuzzy, cloudy representation. But if we loop back, the problem I proposed a couple of slides ago was a bit more rigorous, let's say, where really the constraint that we wanted to enforce is that, we wanted our robot body, like we wanted to be able to compute that its probability of collision, was less than epsilon. But what we instead basically optimized was like a loose kind of like, like multi-objective optimization that tried to enforce basically low collision, but also trade that off with control effort. And so we had a nice follow-up work that's to appear in TRO, where we did some math to basically show there is a way to actually compute more rigorous collision probabilities with these things. And so what we showed is that basically you can interpret the density field of these NeRFs actually as a very particular kind of stochastic process. So we don't have to get too deep into the math, but basically it turns out that this density field can be interpreted as a Poisson point process, which means that you can treat it basically as like a continuous occupancy field. And so what we showed is that actually for a particular robot body B, you can actually compute the probability that it's empty very intuitively. What you do is basically you integrate the density that's contained in your robot set B, and then you exponentiate the negative of that. And what that gives you is basically a true kind of collision probability for your robot B. And so this lets you actually stand up basically a true chance constraint trajectory optimization. So at the end of the day, especially when we made some design decisions to like try to compress these NeRFs and to make everything kind of run in real time, what we had is actually a NeRF-based trajectory optimizer that could run in real time. So these are experiments that we ran in the flight room at Stanford, where we had this kind of 3 pillars. And again, we trained a NeRF kind of offline of the system. And then what we're watching is basically the robot actually planning real paths through this like real environment and avoiding collision, which, I am really excited about this video because this is one of the first kind of like NeRF collision avoidance hardware experiments that we're familiar with. And, I think especially, one thing for a lot of vision projects is this kind of like sim to real gap. And so, I think something I was excited about here is that actually, it's not just with like these simulated meshes I was showing in the last paper, but actually for a real robot with real objects with a real NeRF, this collision probability that we derived actually does give you like nice collision avoidance. So as I end this part of like the kind of computer vision part of this talk, I do want to mention a project that I'm excited about, which is using NeRF objects not for collision avoidance, but actually for manipulation, or we're trying to create collisions on purpose. And so now for a couple different papers I've been working on at Caltech, actually our manipulation stack is NeRF based. So a lot of the, like basically any sort of like grasping project that we've been doing, the first thing we do when we do grasp planing is actually to first build a model of the object. So what you're seeing is basically this like kind of swirl that we have a robot arm do. This is so that you can actually get views that let you triangulate the geometry of the object. And basically the first step in any of our manipulation pipelines is to first train a NeRF, and then use the NeRF somehow downstream to like plan a grasp, let's say, for a dexterous hand. So we have a Coral paper that's in preparation right now that's using like Isaac Gem for like big data grasp planning. But in general, I think this is a really interesting opportunity, is like, you know, because NeRFs are so closely linked with computer vision, because NeRFs give you like nice 3D geometry, I think there's a lot of opportunities that we can pursue as a community, you know, to use these NeRFs actually for like as object representations for manipulation. And I'll talk about this a little bit more towards the end of the talk as future work. So that brings us to the end of kind of the NeRF section of the talk. Now I want to change gears a little bit and talk about some work we've been doing at Caltech that, instead of handling visual or geometric ambiguity, is trying to handle dynamics uncertainty. So changing gears, we're basically going to talk a little bit about kind of like data-driven robust control.
Sorry, can I ask a question here?
Yeah, go ahead.
Yeah.
Well, we hear you very loud though.
Yeah.
Not sure.
Sorry.
No worries.
It's been crazy. Okay, nice videos, nice tools. I want to ask about the risk sensitivity thing. So you talk about risk sensitivity, but the main metric you're using seems to be the probability of something rather good happening. And there's been work on other kind of more generalized risk metrics like value at risk, conditional value at risk, those kinds of things. Do you think that can be applied to your NeRF models?
Yeah, absolutely. I mean, because what we're doing is enforcing, oh man, let's see how many slides I have to go back through. Probably too many. I mean, what we're doing is enforcing like a chance constraint for this trajectory optimization. So for instance, this TRO paper, we're truly enforcing a chance constraint on collision. And so, yeah, I think actually, especially CVAR, I think would be a good fit here, of like, you know, you want, given that maybe collision will happen, you don't want the collision to be too large, let's say. So yeah, it's not something that we've pursued as a direction. We mostly have just been enforcing the chance constraint directly, but yeah, it's something that you can put together. I think one thing I would note, yeah, I'm mentioning risk sensitivity, but actually I don't think anywhere in this talk I use risk metrics like CVAR. Like in general, I'm using it maybe more expansively in terms of like thinking about things probabilistically and trying to minimize like collision probabilities and so on. But yeah, I think that's a good direction forward, is using maybe different risk metrics and maybe looking at how that will perform or how that will change the like qualitative behavior of the system. Yeah, I think is a really interesting direction.
Thank you.
Cool. Any other questions on the vision stuff?
Yeah, actually, I have another question regarding. Yeah,
Go ahead,
can you hear me?
Yeah,
yes.
We can hear
you. Thank you. Can you go back to the slide just now? Yes.
This one?
Slide about probability model. Yeah, I'm just wondering, where does the model come from? Where does the mathematic formulation come from? Is it from intuition or from model of something? Because for me, it's a little bit random.
Yeah.
Like the distribution and point process just come from nowhere. And
yeah.
That seems not the way that we actually interpret the world. So I'm just curious about where does it come from?
Yeah, that's a great question. So I cut it for time, basically, but there's a full derivation in the paper. So to sketch the argument a little bit, what we showed is that if you peel back the NeRF rendering math, so if you look at the ways that, like, so first, basically, the NeRF authors described the way that you're computing, say, like the ray colors or like the ray terminations as like taking expectations along the rays of the camera. But they never really described what distribution they're taking the expectation under. They were just kind of like, you can interpret this as an expectation. And what we show in the paper is that actually, in particular, what that distribution is if it's a Poisson point process. So basically, If you interpret it as kind of this like 3D process that has, for instance, collision probabilities that look like what I'm showing on this slide, then if you take the expectation of termination, so the expectation that these rays are hitting like points of the process as you cast them through the scene, what you get is basically the exact same equations as the NeRF rendering. And so the kind of core argument that we're making is that basically, like, in fact, what this distribution is that the NeRF authors kind of like gestured at is in fact this kind of Poisson point process. And so again, it's kind of a proposition showing equivalence, but that's kind of mathematically where it came from. I just didn't have time here. Like, you have to stand up a lot of mathematical machinery to get there, but that's kind of the core argument.
Okay, thank you.
Perfect. Okay, so I think in the interest of time, I'm going to jump quickly into this kind of robust control stuff for just a second. So for this part of the talk, basically, what I want to do is take the last problem and put it on its head a little bit. So we're going to take our robot B. We're going to basically disturb our dynamics, right? So we're going to start applying maybe an unmodeled disturbance to our robot, but we're going to assume that our constraints are known, right? So now instead of our obstacle set being like random, what instead we're going to have is that actually the dynamics of a robot is random, but we still want to perform basically the same task, right? We still want to keep the distance between the robot and the obstacle set greater than 0. But now again, we're going to assume that we have this like state-dependent disturbance we're applying to the robot. And so what we want is basically, again, to be able to enforce a chance constraint, keeping the robot out of collision. So this changes a couple important things. One is that now our state moving forward in time is the random variable. It's not the like distance of the obstacles. So instead of optimizing, like, say, a cost, we need to optimize like a risk metric. And the second thing is, of course, our dynamics are now going to be stochastic. And in general, we're not going to assume too much about the form of these stochastic dynamics. We're just going to say that they enter in kind of nonlinearly with the other inputs. So in general, this is what I would call stochastic trajectory optimization. And there's a couple of desiderata that we want. Of course, the big thing is computational tractability, right? We'd want to be able to plan, like, to solve this problem quickly so that we can do something like MPC online. Of course, we'd want correctness, right? We want that if we're trying to enforce this chance constraint, we at least are enforcing it like conservatively. Of course, maybe I would say I'm ranking these desiderata in order of importance. I would say a nice to have is actually optimality, right? We would want to ideally minimize the risk, but of course, I think it's not super controversial to say that the first two are maybe more important. So the way that I was trained to solve problems like this is basically doing something like chance constraint programming, right? So again, you pose this all as like an optimization, like a stochastic optimization problem that then you solve with like sample average approximations or something. Typically, there's kind of two issues that you run into practically. I think one is this issue of the union bound. So typically what you need to do, like the constraint we're trying to enforce here is the probability that, you know, jointly across all time that we, like, say, collide with an obstacle is less than epsilon. But the first thing you typically have to do is basically break this into a bunch of independent constraints across time. And so what you do is kind of assume that the states are independent and then bound them using the union bound, which a lot of folks know in practice to be extremely weak, right? You're assuming there's basically no correlation between your states. And so what you get is like really, really conservative behavior out of a system like this. The second one, I think, is a little bit more insidious and maybe one that we don't talk about as much, which is if you remember, the noise model that I put on this system is state dependent. And so what you get is this issue of kind of noise composition, which is saying that basically, for example, if you have your system where you know exactly what your state is at time t, but then you say have a very nice noise model, like you're adding Gaussian noise, then basically what's going on is you look forward in time is that at the next time step, if you have additive Gaussian noise, what you're going to get is like a nice like Gaussian distribution of your state. But then 2 time steps from now, you're going to have to run that Gaussian through your nonlinear dynamics. And so what you can get is kind of arbitrarily complicated distributions of your state, which means that actually solving a problem like this, I mean, there are ways to do this that I think folks are looking at, like scenario methods. But in general, this sort of like arbitrary noise model, like with arbitrary nonlinear dynamics, is really quite hard to solve with chance constraint programming. And so for this project, well, I guess if you go back to our desiderata list, what you're doing is basically taking probabilistic guarantees at kind of the like sacrificing optimality and tractability, right? So tractability is the issue with the noise composition. Optimality is the fact that this union bound is quite weak. And so in general, chance-constrained programming is really prioritizing just the fact that you are trying to guarantee performance. And so for this project, something we were interested in is basically finding ways that we can maybe prioritize, like we could strike a different balance of these optimality. And so what we did was actually use a tool called control barrier functions, which is something folks typically do for deterministic settings in continuous time. The idea is really simple. It's basically if you can enforce this differential constraint, so you can say the rate of change of your constraint in continuous time is greater than alpha of h of x, where, long story short, one example is if alpha is a positive constant, what you're saying is that you want to at most approach the boundary of your constraint like exponentially, then this basically provides you with a safety guarantee deterministically, right? It says that if you are able to enforce this constraint for all time, then you never actually will cross the boundary of your constraint into h less than 0. And so the kind of core idea of this project was saying that we were interested in what happens if you apply a safe control framework like this, not to a continuous time deterministic system, but actually to a discrete time stochastic system. So basically, how much is our safety guarantee going to buy us if we actually have a system that has these state dependent disturbances? So if we go back to our desiderata checklist, basically, we're definitely sacrificing optimality, right? So the sort of way that we're going to enforce this controller using what people call the CBF program, it's only looking one step ahead. It's almost basically greedy instead of the trajectory optimization we're trying to solve. So we're definitely sacrificing optimal behavior, but what we get is basically computational tractability. And what we're hoping for is basically that we get a probabilistic guarantee. So for this project, basically, we were interested in ways that we can provide, even if the system is stochastic, ways that we can actually reason about the probabilistic safety. So the way that we did this is actually using a tool from stochastic processes. So I think if you take nothing else away from this talk, if you like math, I would say focus on this slide, because this is a tool that we found to be quite fun. So we use this tool called Wills inequality, which says that if you have a process that's basically decreasing in time, this inequality is backwards, I apologize. This should be if your process is decreasing, if WT plus 1 is in expectation less than WT, and it's non-negative, then the probability that you instead go the other way, so basically the probability that you rise above some level set lambda is less than the expectation of the process at time 0 divided by lambda. So basically, you can think of this, if you're familiar with concentration inequalities, you can think of this as Markov's inequality, but applied to a stochastic process. And one thing I want to point out is that basically this supremum is over all time. So this is actually an infinite horizon kind of safety guarantee or safety probability. And so the core approach that we took in this project was basically to rescale and shift our barrier function to be able to create a decreasing process in expectation. So what we're doing is basically creating a stochastic Lyapunov function and using this to get a probabilistic safety guarantee. So we have a theorem in the paper. This is an RSS paper that appeared last year that basically does exactly like this, which says that if you enforce a barrier condition on the stochastic system in expectation, then what you get is this safety probability. The unsafe probability is upper bounded by something, which is great. So one thing I want to point out is that basically the algorithm that this gives you is actually extremely useful and extremely easy to implement, right? What we need to do to perform our controller in closed loop is basically to enforce this constraint in expectation, which means that you can, ideally Monte Carlo it, or, if you have nice H and nice, disturbances, you can compute this in closed form. And then second, basically, it lets you get around this noise composition issue, right? Because this program's only looking one step in the future, you don't get this kind of intractable noise problem because you always have, I would say better behaved noise distributions, which is quite nice. So of course, this approach has quite a few sharp edges. One that I really want to highlight for practitioners is this issue of recursive feasibility. So a lot of CBF approaches have this problem, which is basically, you're kind of, let's say, hoping that this program is always feasible. And you have to be actually quite careful to be able to ensure that this program is feasible always over the region of interest that you're trying to enforce safety on. One that I want to pick out a little bit is kind of a problem that's in general present for a lot of stochastic problems or stochastic control problems, which is a modeling problem. So to enforce that constraint on the last slide, you need to know exactly what your disturbance distribution is. And so a problem that we looked at for ICRA this year is actually ways that we can model this disturbance distribution from trajectory data. So to give a practical example, the experiments we did for this paper are basically we took a quadrotor drone. We wanted to enforce a safety constraint, right? Like obviously you want the drone to be above the ground, but then we're going to apply basically this unmodeled disturbance to the drone. So here what we did is we tied a bottle that weighed roughly half the weight of the drone to the drone and want to still enforce the safety constraint. And so basically what's happening is that, we have our system dynamics, like our nominal quadrotor dynamics are quite nice. They're easy to, characterize. But then we're again going to add this like state-dependent stochastic disturbance. And because the state-dependent disturbance is quite complicated, right? Like we're not observing the bottle or passing any information about it to the drone. What we need is basically a way to model this like disturbance distribution. And so the idea is to learn this from trajectory data. So it turns out this problem of learning a disturbance distribution has a name in CS. It's generative modeling, right? So the core idea is that if you have, say, some context data like text, generative modeling lets you generate a distribution of things conditioned on the text that, like satisfy, that basically explains some data that you've collected. So the core idea here is that basically we can train a deep generative model to model our residual dynamics, right? So we can basically train here. This is like a conditional VAE. You can also do things like diffusion, although we did this for speed. But basically, if you collect a data set, so we collected like a minute of trajectory data, you can train a generative model like this that basically can decode noise into different samples that you draw from your disturbance distribution, which lets you basically enforce that constraint we showed a few slides ago. So one thing I want to mention is that we were extremely surprised by how well this worked. So this is showing for a kind of toy model where we had like the state-dependent noise that the CBAE was actually able to capture not just like a fairly complicated like mean of our distribution, but also it could capture the second moment extremely well, which I think is pretty cool. And so what we did is actually apply this to the hardware system I showed. So first, to show we're not cheating, basically, this is what happens if you don't model your disturbance at all, right? So your CBF is being applied to the wrong system. So of course, I think unsurprisingly, it crashes. What's going on is basically Ryan, the grad student, is letting off the controls of this thing. And so what should happen is the safety constraint should keep the drone above the ground. But in fact, because we didn't just model the disturbance, it crashes and bad things happen. I think more interestingly, so if you apply our approach, so if you use the CBF in the generative model, what you get is, of course, like really nice like enforcement of the constraint compared to, I think, interestingly, if you train just a like residual dynamics of the drone using like just a regression task, right? So if you train just like a neural network to try to model, say, the mean disturbance, it's actually not sufficient, right? So the CBF is able to keep the drone from like crashing, but because of the uncertainty that's associated with this model, it still actually doesn't satisfy the safety constraint. And so what I think this says is that basically actually the stochasticity in this problem is important. Like we actually need both the generative model and the CBF to enforce safety, which I think is quite nice. And I think more excitingly, we were able to get this to work in real life in front of people. So this is at a public demo that we did at Caltech. And so again, what's happening is that we're first like flying the drone up to a certain height. We're like kind of spinning the bottle on purpose and then letting go of the controls. And so what's happening is that, again, this like generative model CBF thing is taking over and is able to enforce safety on the drone. So again, you could get this at a pretty nasty initial conditions, and it doesn't really matter. We were able to get the drone to actually enforce safety pretty reliably. And one thing I want to mention is that basically we're applying this now to not just like, nice drone flight with this bottle, but we're trying to push this forward to other like interesting applications like manipulation or in particular bipedal walking. So what we have right now is something that doesn't work. So again, you can show the CBF with no disturbance modeling, like doesn't enforce your safety constraint at all. And what we're doing right now is trying to train CBAEs that again, like say, learn the difference between a reduced order model of walking and what your system actually does so that you can use this for downstream applications like safety. So that brings me to the end of my talk. I'm going to skip future work just in the interest of time. But basically, I think if you take away a few things from this, the one lesson learned is that the generative modeling approach I was just talking about, I think is really interesting. And it gives us ways that we can build uncertain dynamics models like from hardware data that we collect in situ, which I think is a really interesting application that you could apply not just in this like CBF robotic safety context, but you could also apply to things like real to sim gaps and this sort of stuff. Another thing I think that provides us interesting ways forward is using these tools like NeRFs or other kind of like radiance field methods for applications like manipulation. In general, they provide this like nice, easy to train like 3D geometry representation that I think is not being super heavily utilized in robotics right now, but I think could provide interesting ways forward. And finally, just as a kind of nerdy thing, I think these stochastic process tools are quite interesting. And so moving forward, I'm also quite interested in applying them to these kind of safe learning techniques or like these like safe control techniques. And yeah, finding ways that we can basically give probabilistic guarantees for uncertain systems. So with that, I think I'll conclude the talk and I'd be happy to take any questions. Oh, wait, one more plug quickly. I, of course, want to thank my collaborators, and I do want to mention I'm an incoming prof at Stanford at Cornell CS. And so if there are any undergrads, or if you know any undergrads who are interested in this kind of like uncertain, especially like very vision inflected robotics, I would heavily encourage you to apply to Cornell because I'm recruiting PhD students for next fall. Anyway, thank you guys so much, and thank you for having me.
Thank you very much, Preston. Yeah, definitely a great talk and a lot of interesting ideas. Let's open the stage for questions. You can either type in the chat or ask directly. I'll maybe start from a question that was asked before, and I kept it for the end. And it was at the point use which topic, and HM asked, is the navigation method only applicable for static scenes, or can you also apply it to dynamic ones?
Yeah, that's a great question. That's actually a sharp edge and like a limitation of that navigation work is that it's basically applied, it only works for static scenes. So especially one issue with the NeRFs, with the neural radiance fields, is that they kind of bake everything together, right? The geometry of the scene is baked kind of statically in the like the weights of the neural network. And so with those representations, it's hard to move obstacles around like relative to each other. I think one opportunity moving forward is the newer radiance field models, so things like Gaussian splatting, actually are representing everything as these kind of like blobs of color, these blobs of fog that you can move relative to each other. And so I think there's actually like good ways forward on using them to model dynamic scenes or flexible objects and stuff like this. But yeah, at least as we've currently done it, the navigation work that we've done, yeah, does absolutely assume a static scene. And so that's something that would need to be extended.
All right. Any other question for Preston? I have a question. So it's very interesting to see how you're able to trade off, let's say, more fundamental things such as CBFs and more creative ones like the ones you propose with generative AI. I'm curious about your vision for doing these things on board and maybe having robots collaborate and sharing resources when doing this. So are we there yet? Or so I assume some of the case studies you showed were using offline compute.
Yeah. So I mean, at least for the quadrotor CBF work, that was all actually performed on board. So the nice thing about this is sampling. So we chose to use a conditional VAE instead of like diffusion, let's say, for speed. And then the problem, so the nice thing about the CBFs is even though they're like myopic, they're very easy to compute. So even a discrete time we had was an SOCP. And so basically the whole stack for all of this like bottle swinging stuff was running at 100 Hertz on board on a Jetson, which is pretty cool. So yeah, I think that's an interesting question of basically moving forward. My vision is trying to apply this to very like resource constrained systems, right? Like I think the kind of small like mobile robots that I'm imagining, yeah, you can't run a full, huge like, let's say foundation model to do all your forward passes. And so yeah, I think that's kind of the place I'm interested in is like, yeah, how can we both like use data-driven tools, but have them be lightweight enough to run on board real robots? Yeah, which I think is something that we don't ask as much in robotics right now. Like it's either like you typically do learning with offboard compute and, have as much, like inference time as you want, or yeah, you just kind of eschew learning for speed. But I think there's lots of opportunities in trying to put the two together. And that's something I want to push on.
Yeah, that's very interesting, especially I think when you have multiple robots that are probably reasoning in the same way, probably there's a way to share what they're doing with each other and spare some. So I've seen some work in there, and I think it's related and it's kind of promising.
Yeah,
Very nice.
I mean, my advisor Mac, just on that note, has been working a lot on using these NeRFs as like, maps for things like visual navigation. And so one of his students, Javier, wrote a very nice paper on like federated learning of NeRFs. So basically finding ways that if you have a bunch of robots that are exploring the same scene, that are able to communicate over a mesh network, that they're able to build kind of one common NeRF representation using, like, again, federated learning. So I think, yeah, there's a lot of opportunities for this too, of like, for the dynamics, if you have N of the same robot, how can they pool their data to train one model? Stuff like this, yeah, I think is a really interesting way forward.
Yeah, very nice. Thank you. Any other question for Preston?
Yes. Again, I have a question.
Go ahead.
So,
go ahead, Jun.
A more general one, like we're talking about how we model things and about uncertainties, I guess, in model and in perception, like within the whole pipeline. So basically we have two directions. First is that we can try to model things from first principles and these rigorous mathematical formulas. We're trying to find better ways to do that. Or we just lean to the learning method and count down the at least partly black box method. So do you think it's inherently difficult or almost theoretically impossible for us to do everything rigorously? Or it's just we didn't find a good model yet or a good method yet? So which direction are you more lean to?
Yeah, that's a great question. So I guess maybe to pull out a future work slide just briefly. So I'd mentioned that I'm really interested in this like dexterous and hand manipulation. And so I think that's actually a question that I don't really have the answer to, is like basically how much data should be appearing in the pipeline? Like how much, how many things can we model versus how many things can we, like, can we not model and we have to use data for? And so in particular, I've been interested in exploring this question really from a hardware standpoint. So this is our manipulation setup that we have at Caltech. It's just like an Allegro hand with some, like vision-based data estimation for a cube. And I think if I had to give a guess so that I don't dodge your question, I think especially for systems that are really contact rich, some amount of data is going to have to play a part, right? I think these contact rich systems are really chaotic. And so, if you try to model them deterministically, there's just a ton of hyperparameters that you have to tune. There's a ton of things that are almost unknowable, of like if your state estimate is even slightly wrong, you're going to predict a very different trajectory for, say, how this cube is going to move in hand than how it should. And so, yeah, I think for, systems like this that have, difficult to model phenomena like contact, yeah, some sort of data, some sort of like uncertainty quantification is going to have to happen. I think for other stuff, like the quadrotor I was showing, if you don't tie a bottle to it, like using data-driven methods is kind of silly, right? Like we know how to like describe the dynamics of a quadrotor. It's silly to try to just learn a model end to end when we know that it's, basically a double integrator. And so, yeah, I think what the right answer is kind of like very application dependent. But in general, what I'm interested in are ways like, what's happening for the planner that's running in this video, where basically, well, it's not, sorry, I should correct myself, but basically the planner that's running in this video is using Majoko dynamics, which are, not great, but are also kind of model based. And so, yeah, what I'm interested in like moving forward is basically how do you combine something like Majoko that's like mostly right with data to get you, like some residual dynamics that actually capture the behavior of the system. So yeah, I don't know. I think these gray box approaches are pretty promising. And I'm really interested again in exploring this in hardware to say for a real system with real state estimation, what's the exactly like right approach to do this?
Okay, thank you.
Thank you, Jim, for the question. Any other question for Preston? All right, doesn't seem so. I think you had a slide with in the final slide, you had your contact in case you want to reach out to Preston for more detailed questions. Feel free to do so. And I take again the chance to thank you. Great talk. I'm really excited to see where this is going. And also good luck for your move and everything. So we should keep in touch.
Awesome. Thank you. Yeah. And thanks again for having me. This is fun.
Great. And also thank you all for participating, and see you all next week for the next one.